So now we're going to take a look at level curves and level surfaces, and this is going to involve a bit of visualization on your part. So first we're going to explore level curves. So if I'm looking at level curves, and we've already seen from the domain and range what these graphs look like as I start getting multiple variables, there's a second way to visualize a function of two variables, and that's to use what we call a scalar field, where we say z equals the function of x and y. So I've got an x and a y, so something like z equals x plus y. And we say that that height is assigned to xy. So what that means is that a scalar field is similar to a slope field. In slope fields, we had positive and negative little bitty lines that kind of drew to know what the slope field looked like. In three-dimensional variables, a scalar field can be characterized by level curves or contour lines. And that's because it's no longer a slope because I have three things involved. So I don't have a nice pretty slope field. I have actual contour lines that are being created when the values of f of x and y are constant. So for instance, a weather map is an example of level curves. So I've got the different patterns of movement that happen. And this is going to be for pressure, and these are called isobars. So this is an example of how level curves are actually used. So level curves are the 3D equivalent to a slope field. If you're not sure what a slope field is, pause the video and do a quick Google on slope fields, and you'll see what that looks like. Level curves, like in the weather map, represent points of equal pressure, or equal temperature, and the level curves are called isotherms, as we saw in the previous thing. So another common use of these would be to represent electric fields. So I've got the patterns of flowing of electric fields that would then create electromagnetic fields or lightning, things like that. In this type of map, I still have level curves, but I call them equipotential lines. So all these two slides are about is that, hey, level curves are actually used, and they're generated for things like the weather map or for things like the map of the electric fields. Contour maps most commonly are used to show the regions of Earth's surface, and they're related to the height above sea level. So if I think about the Earth's surface as the XY plane, then the height that I am above sea level would be my z value, so it would be the height in 3 dimensions, and this is called a topographic map. So when you start looking at those contour lines, and you might have already connected that to a topographic map. So in topographic maps, here is the image of the geographical figure that I'm working with. And here is what it looks like in topography. So in topography, I'm describing the different sizes and elevations with these contour curves, and you can see the numbers printed on them. So as it goes up, these little lines are describing it getting higher and higher. So that's one of the applications of level curves, is in a topographic map. It's how we describe the height above sea level. A contour map depicts the variable z with respect to x and y. So x and y are the flat surface of the Earth, and then z is how high that surface is according to typically sea level as our benchmark. The space between the level curves indicates that z is changing slowly, whereas a teeny space indicates a rapid change in the height. So let's look back at this example. So here, look at this. This is mostly a flat area. According to the picture, see how wide these lines are? And then see how tight they are right here. So the tighter the line, the faster the height change is happening. So down here, it looks like there's a little slope that's gradual. And so here's my gradual line. And then as it rapids, those little pieces get tighter and tighter. Just like in a slope field, the little lines on the slope field, as the slope changes more rapidly, they get more horizontal. So the 3-dimensional equivalent of that slope line getting closer to horizontal because the slope is changing rapidly is that my contour lines have less and less space between them. So if I'm looking at this hemisphere, this is the graph of 64x squared minus y squared, as shown in the figure. If I wanted to sketch the contour map using level curves corresponding to 1, 2, and 8, look at these level curves. They're pretty systematic, okay? So I'm plugging in 1, 2, and 8 for my constants, and my level curves are pretty simple here. And if you look, I've got 8 on the y-axis, and then I've got 8 on the z-axis because I'm looking for between 2 and 8. So this would be the first rim, which would be flat on this surface, would be 0. Then I'm going to go to a height of 1, and I'm going to sketch my contour line around the three-dimensional shape. A height of 2, sketch my contour line. So the height that I'm sketching is replacing the f of xy right here. And all the way until I actually get to 8. So I should have basically 9 circles if I were to complete that contour map, 1 for each ring around it. So for each value of C, I've got a circular path, and that's just dictated by what it looks like, okay? And if I'm at C a value of 0, my level curve then is the circle with a radius of 8. Goodness, my pictures are messing me over here. So if I look at the 9 level of curves from a flat perspective, so taking this image, imagine just smushing it flat between your two hands, then that would actually show me what it looks like. And notice how the larger those numbers get, the wider the space is, because is the height changing as rapidly as I get higher up? No, it's slowing down. So look at the space between the lines here, and look at the space here. If you're comparing them, very little space here, lots of space here. So it's changing slower. Remember, the tighter the lines are, the faster it's changing. So in level curves, and this is kind of going to be something that's very visual for you again, another example from economics would be the Cobb-Douglas production function. So this is just another example besides topography of where this is used. The function's used to model to represent the number of units produced, and so that's my dependent variable. And then I have amounts of labor and capital as my independent variable. So as I have more capital, then I can hire more people for labor, and that's going to increase the number of units. If I have lots of capital, but I still can't hire people, then I'm still affecting the number of units. And then if I have lots of people to hire, but not enough capital, I can't hire, and my number of units is still affected by those two things. So this is where level curves would be used to describe the relationship between all those three pieces as they move and shift. Now, level surfaces are going to be a slightly different idea. The idea of a level curve can be extended by one dimension to describe a level surface. If a function of 3 variables and has a c that is constant, the graph of the equation is a level surface shown below. So I have kind of this, it's kind of like a megaphone. There's 2 of them put together that I have here. And as my c value shifts, then these cones are going to shrink in width, and that's going to affect my level surface. So these level surfaces are going to be seen with computers, engineers, and scientists. They're working on new ways to view 3 dimensions, like for 3D printers and other applications. So if you're looking at this picture, it's showing a computer simulation that uses color to represent the temperature distribution of fluid inside of a pipe fitting. So I've got my fluid flowing through the pipe fitting, and it's got different things. So that's a great explanation. If I want to describe now, so how do I actually apply level surfaces to something in the real world? If I want to just describe level surfaces of the function 4x squared plus y squared plus z squared. So first of all, I've got 3 independent variables and 1 dependent variable. So I'm going to say that each surface has an equation where this is going to equal c, where c is going to be some constant number. So 4x squared plus y squared plus z squared is 0. 4x squared plus y squared plus z squared equals 1. So if I go back into my GeoGebra, Let's see what that would actually look like as I change the C value number. Oops, let me change that to a number. So let's say 0 equals 4x squared, and be patient, I just need to go back and forth, plus y squared plus z squared. Oh. And be careful when you're typing in here because the exponents will get you. So it wants me to put it over here. So there is if it's 1. I've got this little tiny ellipse looking piece. Let's see what happens as I make it 2. It's growing, right? So the surface of this object is getting larger based on that C value. So I'm no longer looking at the two-dimensional lines. I'm looking at what is the actual three-dimensional object doing as I shift it, and it's growing larger. Now, is that always going to be the case? No, it could be smaller depending on if I had negatives in the equation. So that's what's actually happening. Each level surface would have a different equation based on the value for C. And so these level surfaces are an ellipsoid. So if you look at this, do you notice it's not exactly circular? It's an ellipse. And so each one of those surfaces would be an ellipse that I'm looking at. As C gets bigger, so does that ellipsoid because the radius of that cross section is growing. So the actual surface that's occupied is increasing. And so if I wanted to actually solve this and figure out what those look like for C equals 0, 4, and 6, I would take my original equation, set it equal to 0. That's going to be a single point, and that's why it doesn't show up in GeoGebra. If I did it for 4, then I would have 4x squared plus y squared plus z squared equals 4. Because this is an ellipse, I want to divide all of those by 4 so that I get the equation of ellipse. So when I divide 4x squared by 4, that's x squared over 1. When I divide y squared over 4 and z squared over 4, this is what I get, and this is the equation for my level surface. So when you're taking your level surface, you want to make sure that you're replacing your c with a constant, and then you're finding the equation. If it's an ellipse, you need an ellipse equation. If it's a circle, you need a circle equation. Most other level surfaces are pretty simple. If this was 16, then I'm dividing everybody by 16 so that I can get 1 on the right-hand side. So 4x squared divided by 16, the 4 and the 16 cancel, and that's where x squared over 4 comes from. So this is just an image created with the GeoGebra thing where you can see the different ones all at one time. You probably can do that in GeoGebra. Let's just do a try real quick. If I take this and I give another equation and it's 16, you are able to view the difference in size. So all I would need to do to be able to see this image in GeoGebra would be to plug in the different values of C and to see how it grows. So that's really helpful there.